So for question 2 is, as the pot of tea cools, the temperature of tea is modeled by differential function h for 0 is less than or equal to t, which is less than or equal to 10, where time t is measured in minutes and temperature h of t is measured in degrees Celsius. Values of h of t as selected values of time t are shown in the value above. For letter A, use data in the table to approximate the rate at which the temperature of tea is changing at time t equals 3.5. Show the computations that lead to your answer. So pretty much, we only need the approximate of the rate of change at around 3.5. Looking at the table, we know that 3.5 will be around between 2 and 5, in which their h of t for 2 is 60 and the h of t for 5 is 52. So pretty much, the only thing we must do is plug in h of 3.5, and knowing that we have h of 3.5, which will equal h of 5 minus h of 2 over 5 minus 2, which will lead to 52 minus 60 over 5 minus 2, which will lead to the answer, which is negative 8 over 3 degrees Celsius per minute, which is the rate of change when t is 3.5. So for letter B, is using correct units, explain the meaning of 1 over 10 between the interval 0 to 10, h of t dt in the context of the problem. Use a trapezoidal with the 4 subintervals indicated by the table to estimate this. So pretty much is that we need to explain the meaning of it by using the 4 subintervals on the table, and we need to keep in mind this function looks like the average function formula. So what the problem is asking is the average value of the function h of t on the interval 0 to 10. So since we're being asked to use the trapezoidal sum for 4 subintervals, remember the area of the trapezoid, because it's asking for the trapezoidal sum. So first get what the trapezoidal formula is, or the area I mean, is 1 over t h b1 plus b2 equals area of trapezoid. So let's begin with the first interval, which will be pi times 2, 66, 60. So when you calculate all this, it will be 529.5. This is not the final answer, since we still have the 1 over 10. To get the average value, we need to pretty much multiply this by 1 over 10. And when we do, we will get 52.95 degrees Celsius. Ignore this actually. And now this right here will be the average value of temperature of T during 0 to 10, or 0 during this interval. So for letter C, is evaluate between the intervals 0 to 10 h prime t of t dt using correct units, explain the meaning of the expression to the context of the problem. So pretty much we need to explain this, but we have to explain the h prime of t and integrate it. So pretty much those two will cancel out, and now what we're finding is h of t within the boundaries of 0 to 10. And so since h of t is being evaluated from 0 to 10, we actually only need to plug in 10 and 0. So it will be h of 10 minus h of 0, which will be 43 minus 66, which will equal negative 23 degrees Celsius. So so pretty much the justification of this will be the temperature of the T drops 23 degrees 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 23 t equals 0 to time t equals 10, or 0 to 10. So for D is at the time t equals 0, biscuits with temperature 100 degrees Celsius were removed from an oven. The temperature of the biscuits at time t is modeled by a differential function b, for which is known that b prime of t equals 13.84 e to the negative 0.173 t. Using the given model at time t equals 10, how much cooler are the biscuits than the tea? So, okay, so here you can look back at your table and see that when t equals 0, it was 43 degrees Celsius, and now we need to know the temperature of the biscuits, which we know that they started at 100 degrees Celsius, which is the starting point. The function they gave us is this one. This is the function they gave us. And so, which will be the rate of change of the biscuits. So knowing that, we need to take the 100 and then add that to the integral, since, once more, since 100 degrees Celsius was starting point, and will give us a rate of change. So pretty much, it'll be b of 10 equals 100 plus 10, 0, negative 13.84 e to negative 1.73 t dt. So plug it into the calculator, and we get 34.183 degrees Celsius. So what we need to look how much cooler the biscuits are than the tea. So we will need to subtract h of 10 minus b of 10, because h of 10 was the function for the tea, and b of 10 is the function for the biscuits. So pretty much right here will be h of 10 minus b of 10, which will be 43 minus 34.183, which is about 8.817 degrees Celsius. So the answer is that the biscuits are 8.817 degrees Celsius cooler than the tea, pretty much. Unless you want me to write them, then and that will be your answer for letter D.